Alright, so let's see if we can do 6 dB drop flaw height sizing with phased array, with angle beam sector scans with phased array. And so we took and we scanned the same notch block with the same holes, the 10 thou deep notch, 10, 30, 60, 90, 120, 150, 180, 210, and then the end of the block. And so we're going to walk through all these signals and see if we can do 6 dB drop sizing with the phased array, which that doesn't work either, but it's fun to try. Alright, so we're going to try to do 6 dB drop flaw height sizing with angle beam sector scan phased array. And so this is a scan of the notched block. This is the 10 thou notch, 10, 30, 60, 90, 120, 150, 180, 210 thou deep, and that's the end of the block. And this is at TCG. The TCG was set up with 1/32 inch diameter side drill holes set to the standard OmniScan 80%, up to about an inch deep. And so I think we'll try and use 45. There's the 45 degree angle. And let's go ahead and we'll take a look and see what all these notches look like. I'm going to zoom in a little bit. So this is the ID. These are an ID connected notch. That's the 30. So let's scroll through the whole thing. Okay, this is like taking the 45 degree search unit and marching it right down the notches. 10 thou, 30 thou, 60 thou. We've clearly got a loud corner trap signal and a tip signal. And we could do excellent flaw height sizing from the tips, but that's not what we're attempting to show here. We're attempting to show how the 6 dB drop flaw height sizing technique works. So to look through all those again, there's the 10 thou, 30, 60, 90, 120, 150, 180, and 210. Let's go backwards. There's the 180. Alright, so the depth to that tip on the 180 deep notch is 120, and there it is. We've got, on these corner trap signals, they're kind of loud. They're over 200%, so we can't really do anything accurate with using loudness if the signal goes over 200%. So we need to retake this scan at lower dB. So we retook it at this same setting of reference dB, minus 6 dB. Let's open that file up. And again, these are pretty loud. Here's our 45 degree. And are we over 200%? Yeah, and some are over 200%. So I'm looking at the loudness and the amplitude box over here. Alright, so let's try something with less gain. We took this one with minus 6 dB. Let's look at a file with minus 12 dB. That should get us down so things are not too loud. Alright, let's get that down to the 45 degree. And let's see, how loud is our loudest? Have we gone over 200%? I don't think so, so I think we can use this one. So the 10th notch is not very loud. I can just barely see it up there, but let's try and use this because the others have a little bit more amplitude, and we're going to zoom in. Oops, let me try that again. Alright, so the 10th notch is not very loud. I don't think we're going to be able to use that, so we'll skip that one. Let's go to the 30th notch. And where we have a maximized signal. On the corner trap signal, we got 90.4%. So we can do a 6 dB drop. We'll walk that through there until we get it down to 45. I guess that's approximately 45 there. So let's use our cursors to do our sizing. I'm going to set a reference dB at the ID. We'll set up a measure cursor where we've intersected the flaw, and that gives us a flaw height of 31. Alright, so far so good. That is 30, and that's giving us 31. Right on. Alright, let's move to the 60th notch. There's our maximized signal at 124%. So half of 124 would be 62, so let's walk to where we have 62. I'm going to say it's approximately right there. And that's almost the same as where we were. Okay, so that's going to give us a flaw height of 35 thousandths. So that one is 60, and it's giving us 35. 10, 30, 60, excuse me, that was the 60. Yeah, that's right. All right, let's go to the 90. We'll maximize that signal, 157%. Okay, half of 157 is going to be 77%. Let's walk to where that is approximately 77%. Right around there, and that's 46 thousandths flaw height. That is 90, but it's giving us 46. Alright, let's try the next one. Let's walk that signal to where it's the loudest. 136%, half of 136 is 67%. Somewhere between here and here. So I'm going to say that's going to give us a flaw height of 60. It is 120 and it's giving us 60. Alright, let's go to the 150. We'll maximize that one. That maximizes at 121%. So half of that would be 61%. Let's walk to where we get 61% here. That's going to be somewhere between here and here. It's going to be approximately the same flaw height, 55. So that says it is 55 when actually it is 150. Let's try the 180. Alright, let's walk to maximize that signal. 164. Okay, half of 164 is 82. Let's walk to where we have 82, or as close to it as we can get it. So again, that's going to be approximately that same area, 46 thousandths. So that's giving a flaw height of 46 when it actually is 180. All right, and the last one, this is the 210 deep ID notch, and 133%. And let's walk to where it's 6 dB of that, so that would be about 67%. It's going to be between these two numbers, so again about the same thing, 46 thousandths. So it is 210 and it's giving us 46. So that really didn't work at all either, which is not surprising. 6 dB drop flaw height sizing does not work. All right, thanks a lot. All right, so we tried to do 6 dB drop flaw height sizing with phase drain. It didn't really work. These were our actual flaw heights, and these are the numbers that we got, which they're way off. And I'm reminded of the classroom training that I took at Lavender with a really excellent instructor, Dave Miller. And he said you should always do your sizing, your flaw height sizing, from a tip or from a facet, some physical part of the flaw. But if you can't use anything else, you could use 6 dB drop sizing. Anyway, the thing that people seem to be remembering is that if you can't do anything else, you could use it, which it's not going to really work. It's not going to be accurate. And I don't know why people insist on doing it as if it is good. It's not good sizing. And okay, well thanks a lot.